Okay, this is Zach Austin, and I'm going to continue our lecture on Module 4, Lesson 2, which is about the substitution method for solving systems of linear equations. We had finished the part where we learned the actual technique in class, so we know how to use the substitution method. So what this lecture is actually going to be about is about using this method to solve some application problems. We're going to do a couple of different kinds of application problems today. The first one is going to be distance equals rate times time problems. This problem that you see on your screen right here is about a couple of people who are flying on Delta Airlines flights from Philadelphia to Chicago, and we know the distance is between those two cities is 780 miles. It tells me that on one particular trip they fly into the wind, so fighting against the wind, the trip takes them 2 hours. Going the other way when they're returning, it takes them 1.5 hours instead. Our goal with this information is to find the speed of the wind and the speed of the plane in still air. So I mentioned this was a distance, rate, and time problem. The formula that we're going to use, we definitely need a relationship between those things to solve this. And the formula that we're going to use here is distance equals rate times time. Okay, so in order to really get my information organized here, what I'm going to do first is I'm going to set up a table to put all the pieces in place and to help us build our system of equations that we'll need to solve this. So on this page you'll see a table, like I mentioned I was going to set up before, with distance, rate, and time for the columns in it. And then we've got two different situations. One of the trips, these people are flying with the wind, and the other trip, they're flying against the wind on the way back. So with that in mind, I set up two different rows in my table, one for the with situation and one for the against situation. I've also defined a couple of my variables down there because, you know, the rate is going to be a little bit more complicated than we might think in this particular problem. We're going to need two variables to define it because P is going to be the speed of the plane if there is no wind. If we were just flying in completely still air, then P would be the speed of that plane. W then is the wind speed. Okay, so the first thing let's do is let's think about the rate and how it's going to work in here. It's not just going to be a simple P in either one of these situations because regardless of whether we're going with the wind or against the wind is affecting the speed of our plane, right? With the wind, the plane speed is going to be, you know, the wind will be pushing the plane, right? And so the wind speed will be increasing the speed of the plane. So in order to take that into account, what we need to do is we need to add on a factor to our P to get our total speed. So with the wind, our speed is going to actually be P plus W, right? Against the wind, on the other hand, the wind is going to be fighting against the plane. The wind will be slowing the plane down. And so we need to subtract some speed off to take that into account. So similarly, if we're going against the wind, then I'm going to think of the rate as P minus W. Referring back to the problem on the previous page, in both of our situations we're making a trip of the same distance, right? Whether we're going from Philadelphia to Chicago or from Chicago to Philadelphia, the distance is 780 miles either way. So I can go ahead and fill that in over here. You know, we got a 780 for our distance with the wind or a 780 for our distance against the wind. It's the same either way. It's the same trip, just in opposite directions. They're giving us the time in these problems also. It tells us when they fly into the wind, the flight takes 2 hours, so I can fill a 2 in over here for my T. And real similarly, when they're flying with the wind behind them, it takes 1.5 hours. Now, 1.5, that fractional form is fine for the writing there. We could actually do the math probably okay with that 1.5. But because we have a calculator and it's pretty easy to deal with, I'm going to think of that as a decimal instead. I think I'm going to think of that 1.5 as 1.5. and use that as my time, and that'll complete my table. Now this is useful to us because distance is equal to rate times time, right? That's the relationship we talked about when we first started this problem. So if we go right across the row in this table, we can get equations that are going to form our system, right? Just using that exact relationship. Our first equation for the with the wind column will be 780 equals P plus W times 1.5. Just plugging right into that equation up top there. Against the wind, 780 equals P minus W times 2, and that will give me my second equation. So that's why the table is a good idea here. It helps us organize our information, and once we've got everything in the right spot and we've got our table built correctly, it's pretty easy to go from the table to our system of equations that we're going to solve. Okay? So here on this slide, you'll see the translated equations. I've just pulled all the information out of our table that we built on the previous slide and put it into equation form, right? Nothing new here. But this is the system that we're going to want to solve, and we're going to need to use our substitution method to solve these things. You definitely aren't going to want to graph them. The graphing on this would be difficult, so substitution is the method of choice for us here. There's a couple of different choices for where to go from here. When I'm looking at this, the first instinct of a lot of people is going to be to distribute that 1.5 across the parentheses and distribute that 2 across the parentheses to clear those out. And then to solve from there. To me, though, it's probably a lot easier, since p plus w, that whole thing is multiplied by 1.5, to just get rid of the 1.5 right now. We know that we can get rid of multiplication by dividing both sides, and so that's the first thing I'm going to do here. I'm going to divide both sides of this equation by 1.5. Okay, that'll cancel off these 1.5s over here, leaves with just a p plus w on the right-hand side. Over on the left, we just want to take 780 divided by 1.5, throw that into your calculator, you'll wind up with 520. Okay? And we can do the same kind of thing in the second equation. We've got, whoops, I got a second equation. This should be a minus instead of a plus. Okay, but we can solve this similarly. We want to get rid of that 2 that's multiplied by the p minus w over there. So p minus w times 2, I'm just going to divide by 2 on both sides. Again, that'll cancel that 2 off, leave us with that p minus w by itself there. Over here, 780 divided by 2 will give me 390. Okay, so we've got a new system that's p plus w equals 520 and p minus w is equal to 390. At this point, we're ready to use our substitution method, just like we talked about in class in our last lecture. The first thing that I would, and our first step to solving a system of equations by substitution, is to solve one of the equations for one of the variables. You really can't pick wrong here. All 4 variables are pretty easy to solve for. I'm going to choose the second equation, and I'm going to solve for p in that. It looks pretty easy to me to move that w over to the other side to get the p by itself. So that's going to be my next step here. I'm going to take that w and I'm going to add w to both sides, which will cancel those out, leave us with the p by itself, which is what we want. We want those things solved for p. On the other side, we'll have w plus 390. Okay? And now that we've got that solved, we can take that and we can substitute it in for p in our other equation, right? So we'll have w plus 390 plus w equals 520. Okay, we've got a couple of like terms there. Those w's are like, so we can add those. Move that 390 over to the other side. And we'll have 2w equals 130. Divide by 2 on both sides, and we'll get w equals 65. So what we found there was we found the speed of the wind, which is one of the things that we wanted. Miles per hour, right? Well, we're not done, because we were actually asked for 2 things. We were asked for the speed of the wind, and we were asked for the speed of the plane in still air, which is our p-value. So we're going to need to substitute this 65 back into either one of these equations. Again, a really nice thing about substitution is you already have this equation right here, which is already solved for p, right? So let's take that w value, that 65 that we've got there, substitute it into that equation, and get our p-value. So we'll just plug it in like so. 65 and 390 is going to give me 455. And there's my speed of the plane in still air. Those are the 2 pieces of information that I need. I've got it.